Swayam Prabha. Digital India. Educated India.
Continuing with our discussion on virtual memory, in this lecture we shall be discussing about some of the page replacement algorithms, some of which are actually being used in practice. Okay. So, this is our fourth lecture of this module and we shall be discussing about some of the page replacement algorithms. Now, if you recall, in our last lecture we mentioned the basic motivation behind having this page replacement. When there is a page fault, you are trying to bring the requested page into memory. You see that the memory blocks, the frames are already full. Select a victim page, replace that victim page by the incoming page, and in this process the victim page may have to be written back into secondary storage if the page is dirty, right. This is what we had said. Now, we look at some of the actual page replacement algorithms which have been studied and analyzed and see the pros and cons. Okay. So, we start with the simplest possible algorithm. This is called the first in first out algorithm or FIFO. FIFO says that you keep track of when each page was brought into memory, when each page was brought into memory. Suppose there are 4 pages P1, P2, P3, P4 in a process. Okay, in the axis of time you find that the page P3 was accessed first. So, P3 is 1, then P1 was accessed, P1 is 2, then P4 was accessed, P4 is 3, and then P2 was accessed 4. So, these numbers indicate some measure of the time when each page was brought into memory or accessed, brought into memory, let us say first in. Now, when you select a victim page, try to find out which page was brought in the earliest, which is the oldest page. So, look at the number which is smallest. This is the oldest page. So, P3 will be selected as the victim page for removal. This is the basic idea. So, in this method the strategy is the oldest page, the page which was brought into memory longest back will be chosen as the victim page, and that is the page you remove. And to implement this FIFO algorithm, you can simply have a queue data structure. This you can implement in hardware also. You can have a hardware queue, or you can also implement the queue in software, no problem. So, what you are doing, whenever a new page is brought in, that page number will be entered in the queue, and when you want to select a victim, you will be selecting the victim which is at the other end of the queue. Like in this pages, for example, P1, P2, P3, P4, this is the order in which the processes arrived. So, that is the same order in which they will be put in the queue. So, finally, after all phases arrived, P3 will be here, then P1 will be next, then P4 will be next, and P2 will be at the rear of the queue. So, at the head of the queue you will be having P3. So, when you have to select a victim page, select the page which is at the head of the queue, right. So, as I said, for implementation we can maintain a FIFO queue. You can have a hardware queue, you can also implement in software, because software is justified because you have to invoke this only when there is a page fault, and page fault itself due to page copying and replacement will take a long time. So, you can afford to implement it in software also. So, as I said in this diagram, when a page is first brought into memory, it is put at the rear of the queue, inserted at the rear of the queue. And whenever you want to find a victim page, so for replacement you have to select a victim page, we select the page which is there at the head of the queue. So, in this example P3 was at the head, so P3 was selected as the victim, and lastly when the process P2 came, P2 was added at the rear of the queue or at the back of the queue. Okay. This is how FIFO can be implemented. But now let us do one thing, let us take an example reference string and with some number of frames in memory let us work out and find out how many actual page faults are occurring here. Okay. Let us see. This is an example we shall be working out. First thing is that let us assume a page reference string, the reference string. So, what reference string we are using in this example? We are using a reference string like this, I am writing it down
701203042231201701.
So, this is a long page reference string which you are using in our experiment. And there are two diagrams I am showing here. First, let us look the one at the top. So, the page reference string or the page trace is shown in the bottom. These are the page numbers 7012, as you can see 0304. These are the, so this is the axis of time. This is the axis of time. As the pages are being accessed, we are keeping track of what is the status of the page frames in memory. In the diagram on the top, we are assuming that there are 3 page frames. So, at the beginning when this page 7 was referenced, nothing was there in memory. So, page 7 was brought. So, the status of the memory is 7 blank blank. Next, when 0 was referenced, there is a free space, 0 is also loaded, 7 and 0. Then 1 is brought in, 701. See, whenever you have to bring in a page, I am marking it by red. So, 7 you are bringing in, 0 you are bringing in, 1 you are bringing in, I am marking it by red. Then you are accessing page number 2. You find that out of 701, 2 is not there. So, you will have to bring it in. So, now the question is that the memory is full, you will have to select one victim. So, which one will be selected? Out of 701, which is the oldest page? You look back in time and find that 7 is the oldest page. 1 was accessed just before, 0 was accessed before that, 7 was accessed even before that. So, 7 will be your victim page. So, when you are bringing in 2 here, you replace 7. So, 7 is swapped out. Next, page number 0. 0 is already there in memory, so this does not result in a page fault. So, I am showing it in black. Same thing continues. Next page is 3. Out of 201, you find out which one is the oldest. 0 is the oldest. So, replace 0 and bring in 3. Okay. Then again you are accessing 0. 0 is not there, 231. Find out which is the oldest page out of 231. You see, if you look back, out of 231, you can find that 1 is the oldest. So, you will have to replace 1. So, instead of 1, you bring in 0. So, same thing repeats, I am doing it for all the pages. Then for 4, I am replacing 2 and bringing in 4. For 2, I am replacing 3 and bringing in 2. So, all these are FIFO pages, oldest pages I am replacing. 3, I am replacing 0. For 0, I am replacing 4. 3 is already there, so no page fault. 2 is already there, no page fault. Next is 1, so replace 2 and bring 1. 2, replace 3 and bring 2. 0, 0 is already there, no page fault. 1 is also there, no page fault. 7, replace 0, 0, replace 1, and finally 1, replace 2. This is how you can work out step by step. At every step, try to find out which is the oldest page. If you want to replace it, replace the oldest page, bring in the new page, and if the new page is already there, do not do anything. And here, every time we have to bring a new page in, I am marking it by red. So, just count how many red are there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, there are a total of 15 page faults here. So, with 3 frames in memory, there are 15 page faults. So, in the diagram below, we are working out the same example, but now with 4 page frames. Instead of 3, we are using 4. Now, we expect the page number of page faults to reduce. So, we have worked out the same thing. So, first 7 comes, then 0, then 1, then 2. So, now all the frames are occupied 7, 0, 1, 2. Next reference is 0, 0 is already there. 3 is not there, it is full, you will have to find the oldest page. 7 was the oldest page, replace 7 by 3. Then again 0, 0 is already there. 4 not there, replace the oldest page 0, bring 4. 2 already there, 3 already there, 0, replace 1, bring in 0. Like this, you continue like this. And you see that for this example, you get only 10 page faults. So, with 3 frames, you are having 15 page faults, with 4 frames, you are having 10 page faults. Well, this is what we are expecting, right? As the number of frames increase, we can keep more frames in memory, page fault should reduce. Let us take another example for the same algorithm, FIFO algorithm. Let us take another example. Here our reference string is like this. As you can see, 5, 4, 3, 2, 1, 4, 3, 5, 4, 3, 2, 1 and 1. This is our reference string. So, we are again redoing it for 3 and 4 frames. For 3 frames, similarly we see 5 loaded, 4 loaded, 3 loaded. So, 5, 4, 3 are in memory. You access 2, 2 is not there, replace the oldest page 5, 1 not there, replace 4, 4 not there, replace 3, 3 again not there, replace 2, 5 again not there, replace 1, 4 is there, 3 is there, 2 not there, replace 5, 1 not there, replace 4 and 1 is there. So, you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 page faults. But surprisingly, if you increase the number of page frames here to 4, you find that the number of page fault is increasing, it is becoming 11. So, this example has been worked out also, you see here. this is something which you are not expecting, right? This is anomalous, and this was observed by Bellardi, and this has come to known as Bellardi's anomaly. Bellardi's anomaly says that in some page replacement algorithm, if you increase the number of available page frames in memory, the number of page faults can go up. Okay? That is what Bellardi's anomaly says. Let us talk a little bit about Bellardi's anomaly. As I said, it is a phenomena, or it is an observation where, as I said, increasing the number of page frames results in an increase in the number of page faults, which we are normally not expecting. We are expecting a reverse thing. As the page frame increasing, page fault should decrease, but we are observing a different behavior here. Well, this behavior was analyzed, and something was noted that there are some algorithms which can be categorized as stack based algorithms, and this Bellardi's anomaly can never occur for stack based algorithms, and FIFO is not a stack based algorithm. That is why for FIFO, Bellardi's anomaly may show up for some page reference strings, as we showed in the second example. Now, let us see what this stack based algorithm means. See, in our simulation, so what we did? So, we had the frames in memory, and along the axis of time we were looking at the page references and trying to see whether they are in memory or not. So, at any particular point in time, if we look at the page frames which are in memory, stack based algorithm says for any given point in time, the set of pages which are there in memory for n frames, here n equal to 3, will always be a subset of the pages with n plus 1 frames. If you increase, it will always be a subset, but if you look at the previous example, let me go back. If you look here, for certain cases we will find that it is not so, like let us see, yeah, here it is 354, here it is 1542. In the first cases there was a page number 3, but in the second cases 3 is not there. So, this is not a subset of this. This is not a stack algorithm. So, stack algorithm says that the set of pages in memory for n frames will always be a subset of the pages for n plus 1 frames, and this should hold for all time steps. And if you can ensure that this is true, if you think, obviously you cannot have an increase in page fault for n plus 1, because the same set of frames are there in memory, there cannot be more page faults here, right. But in FIFO, since we are only concerned with the page which was first entered and replacing based on that, so this property is not guaranteed. But in the other methods we shall see, the way we are selecting the victim page, it is automatically guaranteed, right. Okay. Let us look at the second algorithm now, optimal algorithm. Well, I mentioned earlier in the previous class that optimal algorithm is more like a theoretical algorithm. This cannot be implemented in practice, but you can compare the performance of this algorithm against the other algorithms. Here what you do, we select as victim the page, that means we replace the page that will not be used for the longest period of time. That means we are peeking into the future, we are looking into the future time steps and finding out among all the pages in memory, which is the page which will be accessed farthest down in the future. So, better to replace that, because the other pages will be accessed recently. Okay. This is the basic idea, and this method, if you can implement, will guarantee the lowest possible page fault for certain number of frames. It can be proved also, we are not going into the proof, but as I said, because we need to look into the future, it is not possible to implement this algorithm per se, because it requires knowledge of the future, what is the page access pattern that is happening in the future, you need to know about that. So, the question is, why do we need this algorithm then? See, this is an algorithm which has been proved to provide the lowest possible page fault for a certain number of frames. Now, suppose you come up with a new algorithm, you see how many page fault is happening, you compare that number with optimal algorithm and you can tell that, well, my numbers are within 10% of the best. So, optimal algorithm will give you what is best. With respect to that, you can compare other algorithms. That means, this is mainly used as a benchmark for evaluating or comparing other algorithms. Okay. So, let us work out that same page reference string for the first example, for this one as well. So, that same page reference string we have used 701, 20, 304 and so on. So, for the 3 page frame case, in the first case there are 3 page frames. Similarly, 7, 0 and 1 are coming in, they are entered. Then we have 2, the oldest page 7 gets replaced, 0 is already there. So, out of 702 you look into the future, you see 2 is accessed here, 0 is accessed here, 7 is accessed much later. So, 7 will be the victim, remove 7. And next, when 2 is accessed, okay, next 0 is already there, fine, next 3 is accessed. Now, question is, out of 201 which will be the victim? Look into the picture, look into the future, I mean, where is 2, where is 0, where is 1? 0 is here, 2 is here, 1 is here. So, 1 is furthest down. So, replace 1 and bring 3 in its place. So, do this in every step. Among all the pages which are in memory, look into the future page access pattern and see out of these which is the page which will be accessed latest down in the future. Select that as the victim, and the same thing I have followed for all the time steps. And what I have found is that here 9 page faults are happening. Okay. And for 4, similarly we have done, similarly we have carried on, except for example, let us see one step, let us say here, let us say 3, let us look at here. So, right now the memory contains 7, 0, 1 and 2, look into the picture, future, 7, where is 7? 7 is here, 0, 0 is here, 1, 1 is here, 2, 2 is here. Out of these 4, 7 is the farthest. So, you will have to replace 7 and bring in 3. Let us take another one, let us take this one. When this one is coming, memory contains 3024, let us see 3024, all of them are not there, 0 is only there, you can replace any one of them. In the future you find 0 is there, 0 is there, but 2, 3, 4 are not there, any one you can replace. So, I am replacing 3. So, for this if you see, you will see that the number of page frame is 8 and this is the minimum possible. And you can analyze at every time step what is the set of pages in for 3 frames and for 4 frames, you will find that they are subset, it is a subset. It is true for every time step. Let us say for this time step, here we have 2, 4 and 3, but for 4 you have 2, 4 and 3 are already there and also 0 is there. So, it is a subset. So, the same is true for all time steps. You are storing the frames that are accessed in the near future, nearest future, and this naturally the stack property will hold. If it is 3 frames, I am keeping track of the 3 nearest accesses. If it is 4, 4 nearest accesses. So, out of 4 the 3 will automatically come in. So, this will be a stack algorithm. Okay. So, like this it works. Let us look into the third algorithm. So, I said optimal algorithm cannot be implemented because you need to look into the future. So, here what you are trying, we are trying to implement some approximation of the optimal algorithm. See, just imagine you have to predict the future. So, what you can do? You can say that, well, I have seen the past, it happens like this, most likely it will happen in a similar way in the future also. That means, you are using the recent past as an approximation to the nearest future, to the near future. You say that last 3 days there was rainfall, it is likely tomorrow also there will be rainfall. Something like this you are predicting, right? And this has been motivated by locality of reference. What happened in the near past, that is your locality, and locality of reference says that those kind of accesses will again happen in the near future. So, you are predicting the future based on that locality, right. So, here for optimal algorithm we were choosing the victim page as the one which will be used furthest down in the future, but here for LRU we are looking at the past. You are selecting the victim page as the one which has not been used for the longest period of time. That means, a page which was not used recently, which means it is perhaps not in the locality, locality of reference is not holding for that. The pages which are used recently, likely they will be again be used in the near future. That is what temporal and spatial locality says, right. Let us work out the example. That same example, same reference string. So, for 3 page frames you see LRU algorithm gives 12 page faults. Let us work out 7, 0, 1, the first 3 are fine, 7, 0 and 1. So, page gets filled up, then 2. Out of 7, 0 and 1, which is the least recently used? 1 is most recently used, 0 is next recently used, 7 is least recently used. So, replace 7. Then 0 is there, come to 3. Out of 2, 0 and 1, which is least recently used? 0 is here, 2 is here, 1 is here. So, 1 is least recently used. So, replace 1 and bring in 3. Like this you follow. You look back into the future, whatever pages are there in the memory, when they were accessed last. the page which is farthest away, select that as the victim. Similarly, for 4 page frames, if you do, you find that you are incurring 8 page faults. Okay. So, it is of course the same value as optimal, but it is not necessarily true, it will be the same value. For this example, it is becoming the same. But for LRU also, if you see, LRU is also a stack algorithm. If you look at any time step, let us say we look here. Here we have 0, 3 and 2. You have 0, 3, 2 and also you have 4. Take another time step, let us say here, you have 1, 0, 2. You have 1, 0, 2 and also you have 3. So, it is a subset, because the least recently used pattern also will follow this stack property. You are taking the last few least recently ones, and if it becomes 4, the 4th last also will come in addition to the first 3. So, it will be a subset naturally, right. So, LRU algorithm, basically the idea is like this. Okay. Now, let us see how this LRU algorithm can implement. See, this LRU is something which we can possibly implement, because it results in something you can measure in the past. How you can implement this? See, there are broadly 2 approaches in which you can accurately implement the LRU algorithm. First one is using something called counters. The idea is as follows: you have the page table, right? Suppose you have the page table. So, in the page table, you are storing the frame number, you are storing the flags, valid, invalid, dirty. So, let us call it flags. In addition, you are also storing some counter values, count values. Each page table entry will be having a counter value stored. What does that counter value contain? That basically indicates time of use of that particular page. See, in the system you maintain something like a logical clock. Logical clock is something which is updated periodically. It contains some value 1, 2, 3, 4 something. Every time at some event happens, you increase the value of the counter by 1. The idea is that whenever some page is referenced, the value of the logical clock is copied into the page table into the counter field. Content of a logical clock is copied into the counter, so that looking into the page table entry will know what is the last time, last count value when that page was accessed. And when you have to replace a page, you have to select the victim. You determine the entry in the table which has the smallest counter value. That will be the least recently used pages that were used longest in the past. Obvious drawback is that it is expensive to implement, because to find out the smallest counter value, you have to search through the entire page table, search through all the counters, not easy, right. So, theoretically this may be okay, but practically this cannot be implemented because of its high overhead. The other alternative is that here also the overheads are high, that you can use a stack, maintain some kind of a stack of page numbers, like conceptually a stack looks like this, where you can push elements in the stack and you can pop elements from the stack. You maintain a stack of page numbers. Whenever a page is referenced, if the page is already in the stack, remove it and push it in the stack. So, the recently accessed page will always be in the top, and when you want to select a victim, select the entry in the bottom. that is the oldest page. Now, you see, normally in a stack we access in the top, but here you say that you may have to delete something from the middle, take out an element from the bottom. So, implementation becomes very complicated. So, here also, because of the complexity of the implementation, we normally do not implement this, it becomes difficult to implement. Okay? But what you can do, we can implement some approximations. Pure LRU is difficult to implement, but in an actual implementation within the operating system, we need to have a method which is fast, which does not incur too much overhead either in software or hardware. So, what we saw is that there are two LRU approaches using counters and using stack, they are both expensive to implement. So, normally in terms of implementation we do not implement LRU, but some simple approximation of LRU. We consider a couple of methods here. The first method uses something called reference bits. Reference bit means the idea is follows, every page table entry will contain a bit. When you refer a page, access a page, the reference bit will be set to 1. So, initially when a page is brought to memory, all bits are reset to 0. Whenever you access a page, that bit is set to 1. So, each entry in the page table is associated with a reference bit. They are all initialized to 0 by the operating system. Now, actually this is done periodically, because what might happen is that over a period of time the pages will be accessed and you may find that all the reference bits have become 1. So, periodically the operating system can reset all the bits to 0 again, and to select the victim page you search the page table in any order and find out any one page whose reference bit is 0. See, reference bit 0 does not mean it is the least recently used page, because there can be many pages with reference bit 0. Since the last time, whichever pages were accessed, but all other bits are containing reference bit 0. So, you are selecting any one of them. You are not calling them least recently used, but rather you can call it not used recently, because the pages which are used recently, their reference bit have been set to 1. Now, to increase accuracy, instead of a single reference bit, you can have multiple reference bits. Like with each page table entry, let us say I am giving an example, you can have 3 reference bits. So, whenever you are accessing, you set the bit to 1 and all the reference bits you shift left by 1, they are all shift registers. Now, shift register, if you shift left by 1, the advantage is that the oldest page will be having the highest value, you can check which is the largest value. If you can maintain these shift registers in a hardware area, register bank, so all these things can be implemented. So, this method can be implemented with relatively less overhead, it is feasible to implement. Okay? And the other method, this is also some kind of a similar combination of means it goes by the philosophy LRU, but similar to FIFO. This is called the second chance algorithm. Second chance algorithm, as the name implies, you are not replacing a victim right away, you are giving it a second chance. So, how it works? Essentially, it is a FIFO algorithm, FIFO replacement, but additionally it also uses reference bits. Let us say one reference bit. So, using FIFO, first in first out, using that policy, you select a page for replacement. So, when you select a page for replacement, you inspect the reference bit, let us say the reference bit is R. If you find that the reference bit is 0, what does it mean? It means that page which is the FIFO page, it came in earliest, but also R is 0 means it was not used in the recent past. So, you can go ahead and replace the page. But if you find R equal to 1, it means the page is the FIFO page, but R equal to 1 means it was accessed in the near future, in the recent past sometime. It was accessed, that is why the R bit was set to 1. So, in such cases you do not replace the page. What you do? You give the page a second chance, do not replace it. You set the R bit again to 0. R bit was 1, set the R bit again to 0 and move on to locate the next FIFO page for replacement. If next time again this page is selected and now the R bit is found to be 0, then you replace. So, as I said, when a page gets a second chance, the R bit is reset to 0, and if you want to keep track of the arrival time in FIFO, so the current time will be the arrival time. That is how FIFO is managed. So, a page which is used often enough, it will be setting its R bit to 1. So, if it is R bit will be 1, it will never replace that page, because you are replacing that page if it is a FIFO page plus R equal to 0. If it finds R is 1, that means it was accessed recently, it will not replace that page. So, this is better than FIFO. Okay. So, a simple example I am showing here. Suppose these are some pages in memory and the corresponding reference bits only I am showing, and these arrows indicate the FIFO order, that which page came in first. So, at any given time we scan the reference bits from top to bottom. The first, suppose this page is the victim, has been selected as the victim. So, what you find is that this page has the bit set to 1. So, what you do? You set the bit to 0 and proceed with the next one, which is the victim. Like that you proceed. Give it the second chance. Okay. So, I am not going into much detail of this. And then next question is regarding allocation of frames. Now, we told earlier each process needs a minimum number of frames to start execution. It can be 2, 3, 4 up to 6, depends on the complexity of the instruction set. And when a process starts, certain number of frames are typically pre-allocated before the process starts execution. But once the process starts execution, it may be requesting for further frames, there will be page faults, some new frames will be brought in. Now, the question is, how do you select the frame to be replaced? Like what I am trying to say is that there can be multiple processes running, let us say Pi, another process Pj. Pi may be allocated certain number of page frames in memory, Pj may also be allocated certain number of page frames in memory. Suppose Pi is running and Pi has generated a page fault. So, it needs a new page to be brought in. Suppose the memory is full. When I have to select the victim page, how do I select? Do I select a page among the ones which currently are held by Pi, or do I select the victim among all the pages Pi, Pj altogether? That is referred to as global versus local replacement. Let us look into that. Global replacement means whenever a page replacement is needed, a process selects a replacement frame from the pool of all frames. Like I am a process, you are a process, I need one more page I can replace one of your pages from memory and I can bring one of my frames. So, from the pool of all frames I can select any one of the frames, not necessarily my own pool, it can be from your pool also. So, as I said, in this method a process can take away a frame from another process. Because of that, the execution time can vary greatly. For example, you think about your process, you run it once, you run it in a certain time t1. Next time you run it, maybe another process is running which is taking away pages from you. So, there will be a lot of page faults for your case. You will see that maybe now your time is t2 which is much greater than t1. So, your execution time can vary greatly. But the advantage is that because you are now able to take away frames from other processes which possibly may not be using it, in general it can result in higher throughput. Your process will be running faster. So, this is global replacement. Vis-a-vis, you can have something called local replacement, where the process is selecting the replacement frame from its own set of allocated frames. Suppose I am a process, I have been allocated 10 frames, I need a new frame. So, I will be selecting as victim one of those 10. So, I will not be disturbing the other processes. So, first thing is that this may lead to poor memory utilization. Why? Because you see, I am replacing from my own set of 10, but maybe some other process is occupying many frames but not using them. I could have used them. Okay. So, generally this may lead to poor memory utilization because I may be using all my 10 frames very frequently, but still I am replacing one of them, and I am not disturbing the other processes. That is why the performance of individual processes become more consistent in this case. This is one thing. And lastly, there is one phenomena called thrashing. Let us talk about this. Thrashing is something, is a state of the system, you can say, where a process spends more time handling page faults. Due to some reason, whenever you start running a process, you will find that there is a large number of page faults. That means there is a frequent transfer of pages from disk to memory, memory to disk. So, the performance of the process becomes very slow, because most of the time you are incurring disk access which is requiring of the order of milliseconds of time as compared to nanoseconds for memory access. So, essentially a process spends more time swapping pages rather than actual accessing memory and execution, which can lead to very low CPU utilization. And thrashing can happen when you are not giving enough number of pages to a process. Like for example, suppose I am a process, I need 8 pages. All these 8 pages are executing very frequently in a loop, but if I take away even one of those pages, there will be a lot of page faults. That page which I have taken out will be requiring again in the future. I will be bringing in, I will be replacing another page, that will again be required in the near future. Again there will be a page fault. Large number of page faults will be there. So, this happens when a running process is not being allocated enough number of pages, which will cause very frequent page faults. Now, the graph on the right, you just study this. On the x axis we are plotting degree of multiprogramming. Degree of multiprogramming means number of processes in memory. And on the y axis we are plotting CPU utilization. See, normally we see initially when we increase number of processes, the CPU always will be having some process to execute. Even if a process gets blocked, goes to the waiting state, some other process will always be there. So, CPU utilization will steadily increase. But beyond the point, as you can see that the utilization is sharply dropping. Why it is happening? Because now I have loaded so many programs in memory that I am not being able to give sufficient number of pages or frames to the running processes. So, they are now thrashing, they are generating lot of page faults. So, thrashing starts from certain point in time, after that the CPU utilization drastically drops. The main problem is that the operating system does not know what is happening, right, who is thrashing, who is not thrashing. It just observes that suddenly the CPU utilization is starting to drop. So, what the operating system will think that, well, I feel there is not sufficient process in memory, that is why the CPU utilization is dropping. Let me bring in some more process. So, if you bring in some more process, the number of pages will further be reduced from other processes. The problem will increase further. If it adds more processes, this will increase the degree of multiprogramming and the problem will become even more severe. So, once a thrashing starts, the problem becomes more and more complicated after that. Okay. So, with this we come to the end of this lecture, where we have discussed some of the page replacement algorithms, and at the end we discussed the problem of thrashing. So, we shall be continuing our discussion in the next lecture, where we shall be talking about some other aspects of virtual memory, following which we shall be moving to our next module on file systems. Thank you.